Okay, so today in this video we're going to have a look at kinetic energy, and we're going to see how we can formulate an equation to describe the kinetic energy of a moving object. Now, unlike with gravitational potential energy in the previous video, which we had almost a relative value, we were just looking at the change. With kinetic energy we were going to look at an absolute value, because objects do start from rest, so the kinetic energy they gain is an absolute value compared to that rest value, which would of course be 0 joules. Only seems right when we're looking at kinetic energy to look at our largest and fastest engine. So we'll have Gordon now on display for this one. Right, what we need to do is look at a little bit of maths behind this one. So what we're going to do is consider the work that's done by a force to accelerate an object from rest. So remember, any object that is at rest will have 0 kinetic energy, and a force is therefore used to accelerate the object. Think of Newton's laws. So a resultant force will accelerate the object, which means it's done work on that object to accelerate it. So our starting point is back to work is force multiplied by displacement. And we know that force is mass times acceleration, so the work done is mass times acceleration times displacement. Okay, if we go back to our Suvat equations, you might remember one that looked v squared equals u squared plus 2as, one of our significant uvat equations. And we know that u in this situation, we're saying it's from 0. It started from a value of at rest, so our u value here is 0. So we've got v squared equals 2as. So let's put that in, because we started from rest. So if we rearrange that, we've got as is equal to v squared over 2. And up here we've got as, so we can substitute this term, v squared over 2, into the equation here. So we're left with v squared over 2. And that's the work done on the object. Okay, more commonly, that was written out as a half times m times v squared. And as the work done has all been converted to kinetic energy from rest, that means the kinetic energy of any object would be equal to the work done in accelerating an object to a speed of v from rest. Kinetic energy is given quite neatly by a half times mass times velocity squared, giving us a very happy record-breaking Gordon.